p-value is one of the most widely used numbers in statistics, and also one of the most widely misunderstood. If you ask 10 working researchers to state the definition precisely, you will often get 10 subtly different answers. The issue isn't that the definition is hard. The issue is that it is almost always taught in words, when it is fundamentally a picture. In this video, we're going to draw that picture from the ground up, so the definition becomes a visual object you can reason about rather than a verbal formula to memorize. To understand a p-value, we really only need three ingredients: the null hypothesis, which we'll treat not as an abstract claim, but as a generative mechanism; the null distribution, which is the set of outcomes that mechanism produces; and the observed statistic, which is the single number our experiment actually returned. Once those three pieces are in place, the definition of a p-value follows directly from them. Let us start with the simplest possible example. Suppose we want to decide whether a coin is fair. The null hypothesis is the statement that the probability of heads is 1/2. That sounds like a philosophical claim, but it is better to read it mechanically. The null hypothesis is a machine that flips a fair coin 20 times and reports how many heads it observed. The machine is fully specified, and crucially, we can run it as many times as we want. Imagine running this machine once. We might get 12 heads, or 9, or 14. Run it a second time, and the answer will typically be different. There is no single correct outcome because the machine is genuinely random, but the variability is not arbitrary. If we record the head count across many runs, a structure begins to emerge. If we plot the head counts from 1,000 of those runs on a histogram, we see something specific. Low counts and high counts occur rarely. Values near 10 occur most often. As we increase the number of runs, the histogram smooths into a clean shape. This shape is the null distribution. It is the distribution of outcomes we would expect if the null hypothesis were true. Every question a p-value answers is ultimately a question about this object, which is why it's worth drawing it explicitly before doing anything else. For this setup, 20 flips with a head probability of 1/2, the null distribution is the binomial distribution with a trial count of 20 and a success proportion of 1/2. It is a real, named distribution with a closed-form expression, and it is worth calling by its name. Both objects describe the same distribution. The formula gives the exact probability of each outcome, while the histogram makes it immediate which outcomes are common and which are rare. We will work with the histogram throughout because the geometry of the p-value lives on that picture. Now we run an actual experiment. We flip a real coin 20 times and we observe 17 heads. That observation is a single number. The natural question is whether it is consistent with the null hypothesis. Geometrically, we can place that observation directly on the histogram we just drew as a single point on the horizontal axis. And once it sits there, the question becomes much sharper. How surprised should we be to see 17, assuming the null hypothesis is true? We are no longer asking whether the coin is fair in any philosophical sense. We are asking how far into the tail of the null distribution our observation has landed. That question has a numerical answer, and that answer is the p-value. Formally, the p-value is the probability of observing a result at least as extreme as the one we got, assuming the null hypothesis is true. Visually, it is the shaded tail area of the null distribution, starting from our observed value and extending outward. For 17 heads under a fair coin, that area is about 1 in 1,000. It is not a mysterious quantity. It is a specific region of a specific picture, and its numerical value is just the area of that region. The geometry becomes clearer if we imagine sliding the observed value across the distribution. When the observation sits near the peak at 10, the tail area covers roughly half the distribution, and the p-value is about 1/2. As we slide toward the edge, the tail shrinks and the p-value shrinks with it. At 17, 1 in 1,000. At 20, essentially 0. The p-value is nothing more than this tail area, evaluated at whatever value our experiment happened to produce. There is one subtlety worth being careful about. The word extreme can mean two different things depending on the question we are actually asking. If we only care whether the coin is biased toward heads, we shade the right tail and nothing else. This is a one-sided p-value. If we care about bias in either direction, heads or tails, we shade both tails symmetrically. This is a two-sided p-value, and in most applied contexts, it is the quantity people mean by default. It is worth pausing to say clearly what a small p-value does not mean. A small p-value does not mean the alternative hypothesis is true. It does not mean the effect is real. And it does not measure the size of the effect. It tells us only that our observation is unlikely under the null. Whether that unlikeliness should change our beliefs about the world depends on things the p-value cannot see: prior evidence, effect size, study design, and how many hypotheses we tested along the way. Let us see how this scales to a continuous example. We run an A/B test. Group A converts at 12%, Group B at 14%. The question is whether Group B is genuinely better or whether we simply got lucky. We summarize the difference with a single number, a test statistic. Under the null hypothesis that the two groups are drawn from the same underlying distribution, that statistic has its own null distribution, centered at 0. The logic is identical to the coin. We draw the null distribution of our chosen statistic. We compute the observed value from our actual data. We place it on the distribution. We shade the tail. We read off the area. The picture is structurally the same. Only the distribution has changed shape, because the statistic is now continuous rather than a count. The formal definition that appears in every textbook now has a visual partner. The p-value equals the probability that the test statistic t is at least as extreme as the observed value TOBS, conditional on the null being true. Every symbol in that expression points to something concrete. T is the random variable that generates the null distribution. TOBS is our marker. The inequality defines the tail. The conditional bar is the assumption that makes the whole picture well-defined in the first place. There is a property of p-values that tends to get skipped in introductory treatments. If the null hypothesis really is true, the p-value itself is a random variable, and its distribution is uniform on the interval from 0 to 1. This is a consequence of the probability integral transform, a standard result in probability theory. It means that under a true null, simulated p-values are evenly spread across the unit interval, not piled near 0, not piled near 1. By construction, 5% of them will land below 0.05. This leads directly to the problem of multiple testing. If we run 20 independent tests against true null hypotheses, we should expect roughly one of them to return a p-value below 0.05 purely by chance. This is not a flaw in the method, it is a direct consequence of how the method is defined. The practical consequence is that a single significant result drawn from a large pile of tests is, on its own, very weak evidence. Corrections such as the Bonferroni adjustment or the Benjamini-Hochberg procedure exist precisely to manage this, and in that setting, they are not optional. The p-value provides a yes or no verdict about a single null value. A confidence interval does something more informative. The 95% confidence interval is, precisely, the set of null values we would fail to reject at the 0.05 level. It is the same picture we have been drawing throughout the video, but shaded from the inside rather than from the outside. When we report an interval, we give the reader the full range of parameter values consistent with our data, rather than a binary judgment. A professor of mine used to argue that in most applied settings, a confidence interval is more useful than the hypothesis test on its own. The reason is visible in the picture. A p-value collapses everything we know about the effect into a single decision boundary. An interval preserves the uncertainty. It tells the reader not only whether a non-zero effect is plausible, but also how large that effect might be and how wide our uncertainty around it really is. That additional information is usually what the reader actually needs. There is a separate and deeper question that the p-value was never designed to answer. Given the data we observed, what should we now believe about the world? That question sits in a different framework, and we will take it up in the next video, where we build the Bayesian perspective from the same kind of geometric starting point. Until then.